Okay, welcome students. Today I want to give a short tutorial about discounting cash flow. So the DCF method. And let's say, what have we learned until so far? Let's say the discounting cash flow method we can use in several instances. So for instance, we used it with normal loans, specifically mortgages. We used it to value bonds. And we used it to value stocks. So let's say these three things we're going to value with the discounting cash flow method. First of all, what is the discounting cash flow method? It was this method that helped us to value financial projects or financial products. And in that sense, what did we learn? We learned that money in the future is not the same as money in the present, because let's say of this time value of money decreases in purchasing power over time. How should we deal with this problem? So more in the sense, like the whole idea is with the discounting cash flow method, usually we invest now and we get returns later on, let's say after 1 year, after 10 years or after 3 months, whatever the case may be. This is comparing apples with oranges. Why? Because let's say money in the future should be altered or adjusted, discounted is the word, to bring it to the present. And in the present we usually make decisions, and those future cash flows we bring to the present. So the whole idea was that we said, okay, a present value is nothing but a cash flow at year 1, a cash flow at year 2, and a cash flow in year 3. And let's say someone with no training in finance would say, we just add these 3 up and then we have our present value. No, you say now we should alter this, we should discount this by 1 plus r, while r is, let's say, the discounting rate. 1 plus r to the power 2 and 1 plus r to the power 3. These denominators are, let's say, the discounting factors, and the further we away are from the present, so the further in the future, this discounting factor, this denominator in the equation becomes larger. Because if you cube something, the number becomes larger than if you take the square root, then if you to the power 2, what was the English word for, let's say, yes, just squaring. Yes. So more in the sense, like, this is the whole idea. So these are, let's say, adjustments to bring them to the present. And this discounting factor we perceived as, let's say, the real rate, a compensation for expected inflation, and it's also a compensation for risk, for instance, default risk. So for instance, Greek bonds have a higher discount rate. Why? Because the default risk is much larger than, for instance, on German bonds. Yes? So actually, this is what we discussed. Now let's look at, let's say, the first one that is on the board, loans. So for instance, if we take the specific loan, a mortgage, and what is specific about it, let's say, mortgages have collateral. So a house usually is the collateral to the mortgage. So if you don't pay the mortgage, the bank can put its hands on the house. So if we talk about mortgages, let us value it. And let us talk about a specific form of mortgages, an annuity mortgage. And what is the structure here? What is the structure? The structure of an annuity mortgage is the banks gives you the loan now in the present to buy the house, and you will say, and you will promise to the bank, for the next 30 years, because usually mortgages are standardized at 30 years, I'm going to pay you each month an amount of money to redeem this loan and to pay you interest. So actually what we can say is, let's say, let's call it buy house. This is in the present, buy house. This is a present value. And what are we saying? We're going to pay you an annuity plus an annuity plus an annuity plus an annuity 360. So hopefully you immediately see this 360 comes from mortgages are standardized at 30 years here in the Netherlands, and you pay it monthly. So this is nothing but 30 times 12, 360 payments. This is a payment that's going to take place after 30 years. This is next month, if we buy the house tomorrow. So more in a sense like, this should be adjusted by 1 plus r, 1 plus r to the power 2, 1 plus r to the power 360. Right? So this is actually what we have done. A constant stream of cash flows, because this is, let's say, the prime feature which we already discussed in class of an annuity mortgage, that, let's say, the redeeming, so the paying back of the loan, and the interest rate payments are summed up together as a total amount, which we call an annuity, which stay constant over the next 30 years. So each month you're going to pay the same amount. Now this is very nice because, let's say, this completely is congruent with the structure we already discussed. So more in the sense like, if we want to do this and we want to value this, how should we do it? Not that hard, because, let's say, we know that we can do this in an easier way. The present value, the money you get from the bank now, can be expressed as this string of 360 payments, each discounted for the period it's in. But you can also write it like this. And we've done this already. This formula sums up this whole string. So here again, with this discounting of cash flows, we can come up to this annuity, because we usually know the present value. Yeah, that's usually the price of the house. And this discounting factor. So more in a sense, this is how we can, for instance, calculate this annuity. This is how we use these discounting cash flows concerning mortgages. Next part. Next part is, let's value bonds. Bonds have the same structure. Let me get rid of this formula, because what is a bond? A bond is a piece of tradable debt. So usually a company wants a large sum of money, let's say 1 billion, and they slice it up in small pieces of 1,000. Any investor can buy this piece, let's say this bond, each year, for instance, for the next 10 years, he gets his interest rate, which we now call coupon. And in the end they get the money back, which we usually call the face value, right? So actually the structure of a bond, so bond price, is again the same. What is the idea? I get a coupon in year 1, a coupon in year 2, and let's say this is a 10-year bond, a coupon in year 10, and in the end, in year 10, I get my money back. So that's called the face value. I'm not going to, let's say, elaborate here on, let's say, the theory of talk about zero coupon bonds, etc. But we all discussed this, how bonds are quoted in the newspaper, etc. You should know this by now. But I'm here now discussing the general structure. Here a constant string of cash flows. Here again a constant string of cash flows. Coupons, which should be altered because our strategy was we want to value things in the present because we handle and make actions in the present. So what is the price of those 10 years of coupons and we get our money back? Oh, nothing but the same deal as we discussed. This is our structure, this is bond valuation. And let's say, how do bond prices vary? How can they fluctuate? Because let's say this discounting factor, which is usually called with bonds, the yield to maturity, changes. For instance, because let's say in year 5, inflation expectations change. So this is why the bond price can change. But let's say it's all within this basic DCF method. That we would say yes, just a constant string of cash flows and we discount those. So this is usually called yield to maturity. Again, depending on, let's say, the real interest rate, expected inflation, and also the default premium. So for instance, if the default premium increases, the yield to maturity increases and the bond price will drop. Why? Because let's say the denominators become larger, so the sum as a whole becomes smaller. So let's say, let's sum this up. We can do this the same style as we done for the mortgage, and it is nothing but, it's a coupon and then this part here sums up this complete part here, right? Plus this thing we have to do single-handedly. Why? I write it like this, and then I should write this T also as a 10. This is, let's say, our basic formula for plain vanilla bonds. Same deal. This is, let's say, the discounted value of, let's say, this string of coupons, those interest rates on those pieces of tradable debt, and this is, let's say, our face value, which we discount. Let's say, this is again the structure, so let's say we've done many exercises already on this, but I want you to see, let's say, this discounting cash flow method, we use it everywhere. So we now look at loans, and specifically at annuity loans. So linear mortgages we discussed, but they are different. But let's say if you have an annuity loan where the redeeming of the loan, so the paying back of the loan, and the interest rate payments together are summing up to one annuity which stays constant over time. This is bond valuation. Now our last part is going to be about stock valuation. And I'm going to do this now. Stock valuation, same deal, only we have to make some stronger assumptions. Okay? If you have a stock, so this part here, this one, if you have a stock, actually what you have is, let's say, an ownership entitlement of the company. So let's say if there are 100 stocks, you have one, you're a 100th owner of the company. And what does this mean? It means that you are also this portion entitled to the profits. So more in a sense, like if you're an owner, you're entitled to the profits. You can attend shareholder meetings. But I'm not going to talk about, let's say, stocks theoretically, but more the discount and cash flow method. What is the price of a stock? And if you look at this method we have done already, the discount and cash flow method, what you should see, then you say, okay, what can we discount with stocks? What can we discount? Now those dividends, those parts of those profits that are cashed out to the owners. So, for instance, we can say, if we have a stock, we get a dividend. This portion of the profit for the stockholder, dividend 1 plus dividend 2. And the assumption is that we keep this stock, or I should say, the company will exist until eternity and will pay out to whoever who may own the stock this dividend. So this is actually, as they call it, a perpetuity. So div infinity. Let's say this is a little bit of a stretch. We already discussed this. Let's say we already had difficulty finding companies that are 100 years old. They exist. Companies that are 200 years old, yes, very hard to find. So more in the sense, until this infinity, it doesn't matter. We'll come to that later. What should we do with it? Again, discount this and discount this to the power and discount this to any and discount this. So again, we bring this to the future. What should you realize? If the numbers, if you are the further away in the future, this part of the formula, the denominator, is going to dominate. This number becomes so large that the number as a whole is practically zero. So more in the sense like those Beginning dividends are very important, but let's say if we're in year 100, even in year 50 already, that would say, yes, this denominator is dominating, let's say, of this portion of the formula, so it doesn't matter if we really know that there are companies that are 560 years old. Actually, we don't care. And so, let's say, those future prospects, let's say, I don't know what next week will happen, so let's say, what of in year 26, in the future will happen, yeah. Doesn't involve so much the formula. Okay, so this is what we have done. If we imply that dividend 1 and dividend 2 is dividend n, so there is no growth in the dividend, then the formula for this endless string will come up to the stock price as nothing but the dividend divided by R. So let's say I'm not going to prove this. You can do this by a very easy sequential mathematics, but let's say we just assume it. You just have to believe me. If, let's say, t goes to infinity, then let's say this formula will arise if the dividend is constant. So dividend 1 is dividend 2 is dividend n. Yes? So another thing we discussed is, let's say, okay, we have a stock and we want to price it. What do? We just discount those future dividends. And we also implied that the dividends stay constant over time. The next step we can say, we can spice this formula a little bit up. They will say, okay, this is a company that is growing, and let's say their profits are also growing, so maybe there is growth in the dividends. So this is not a company, for instance, that is in a saturated market with constant dividends. No, this is a company that still grows. So if the dividend grows, how does it work then? Now, this still holds, but the only thing that differs now is that we can say dividend 2 is nothing but dividend 1 times some portion of growth, let's say 2%, 3%, and dividend 3 is nothing but dividend 2 times 1 plus g. You probably already imagine what will happen, because let's say it stays here dividend 2. It also stays here dividend 2. So dividend 2 is the same as dividend 1 times 1 plus g. So if we, let's say, substitute this, we can write down dividend 3 is nothing but dividend 1 times 1 plus g times 1 plus g. Now you probably get the picture. We've done this. This becomes this. So actually what we can write down, we can generalize this, that we say dividend n is nothing but dividend 1 times 1 plus g to the power n minus 1. If we do this here, so let's do it. What do we get? So this is dividend 1, and let's say make this dividend n. This is dividend 1 times the power 1 plus. If we do this again, this formula comes to the following. T goes to eternity, and the formula will be the price of the stock is dividend 1 divided by R minus G. And let's say the price now is dividend 1 divided by R minus G. So it's a little bit different from the constant growth model, because the constant growth model was depicted as this, dividend divided by R, and there is no index for the dividend. Doesn't matter because it always stays the same. While here it is, today's stock price is next year's dividend or the coming dividend divided by R minus G.